Okay, so the next lecture is about fundamentals of logic. All right. So, what are fundamentals of logic? So, let's first try to understand what's happening here. So, these are the topics we are going to explore. But again, I mean, without having what these topics are, I mean, like, we'll come back to this. Okay. So, logic. So, the idea is we'll have statements. Okay. So what are statements? So statements are basically declarative sentences which are either true or false. So you can assign a value to it. Yeah. So so declarative sentences that are either true or false are called statements, and the statements basically have value either true or false, right? Not both. Yeah. If that happens, then that's not a statement. So for example, it is raining. Yeah. It is a statement. Right? So, well, depending on at this moment, is it raining? The answer is yes. So so in that case, it will be true. Yeah. If it was not raining, then it will be false. Yeah. So you see, it's a statement and it has a value associated, true or false. Okay. Similarly, chicken eggs are green. Yeah. So this is a statement, and the value of this is false. Right. I don't think chicken eggs are green. Right. I hope so. Unless they've gone bad. Right. So that is the idea behind the statement. So in logic, the statements are either true or false. Yeah. There's interesting aspect of so-called quantum logic where statements can be in between. We are not going to explore that in this course, right? We are too, like, have you heard about the Schrodinger's cat, which is in superimposition of being alive and dead both? But this is not our concern here, okay? In our case, if you have a statement, it's either true or false. Okay. So not everything said out is a statement. For example, what time is it? This is not a statement, it's a question, all right? Or go turn off the light. This is a command. This is not a statement. All right. Or wow, that's not a statement either. All right. So we have some intuition now of what are statements. All right. So first of all, is this a statement? Sky is blue. So it's a statement, right? What is capital of France? Is it a statement? No. Why? Because it's a question. It's not a statement. All right. So now among statements, there is a concept of primitive statements. So primitive statements are statements which cannot be broken further. Yeah. For example, my name is Vijay and I'm an instructor at FIC. This is a statement. It consists of two statements. My name is Vijay, one. And then another statement is that I am instructor at FIC. And then we are joining these two statements. So this is an example of a non-primitive statement. Okay. So what is a primitive statement? Primitive statement is a statement which you cannot break it further into smaller. For example, the number X is an integer or 5 is an integer. Okay. That is a statement. All right. It cannot be broken further down into a primitive or smaller statement. Okay. Now, so our goal is actually, or the goal of logic is to combine statements or combine primitive statements and then see what are the values associated with it, whether they're true value or false value. Okay. So let's see. So statements made up of two or more primitive statements along with the logical connectives are called compound statements. Okay. So again, there are primitive statements and they are connected with each other. All right. What are the connectives we'll be interested in? Not, and, which is also called conjunction, or, which is disjunction, XOR, which is exclusive or, implication, and biconditional. Okay. Let's not worry about looking at them right now. Let's go through each one of them one at a time. Okay. So first statement is the following. So if we have a P as a proposition or statement, then the statement that it is not the case that P is also a proposition, it's called negation. and it is denoted by, if P is a statement, negation of that is denoted by not P. Is that okay? So, for example, let's make a statement. It is raining. For example, this is my statement P. Yeah. So then the negation would of this will be what? It is not raining. Okay. So this is the idea behind what the negation of a statement. Okay. Now, for every of these logical connectives, we will talk about the truth table. All right. So what is a truth table? So in truth table, what you do is you analyze all the possibilities for something, right? So for example, if I have a statement P, and then what is negative? So now if you look at statement P, the statement P can have either true or it's false, right? Isn't it? Yeah. So in that case, negative P will be what? If it is true, then it will be false. If it is false, then the negative P is going to be true. So this is one example of the truth table of, or this is the truth table for the negation. Yeah. So what you notice here is the following. If P is a statement, we are not already having a truth value to it associated with it. We are analyzing all possible values associated with the statement P, right? Because statement P could be true, could be false. We don't know, right? So, but the truth table basically displays all the displays the relationship between the truth values and the proposition. Another way to do this is basically people take true to be 1 and false to be 0. So in that case, negative P will be 0 and this will be 1. All right. So this is the first of the logical connectors. Let's look at a few more. Then there is another statement called conjunction. So what is a conjunction? Conjunction. So let P and Q be propositions. Now in this case, we are combining what? Two propositions together. So let P and Q be propositions. The statement P, so conjunction is basically denoted by this sign, wedge sign, and it is read as and, okay? So when I'm reading this, I say statement P, so I read it as what? P and, so I'm reading this as P and Q, okay? So what is the conjunction of two statements? So conjunction of two statements is the following. So if you have two statements or two primitive statements, I mean, they don't need to be primitive, but if there are two statements, then P and Q is true if and only if both of them are true. Yeah, if both of them are true, then it is true. Otherwise, it's always what? It's false. So that is the meaning of a conjunction. We will mostly use and. Okay. So when I read this, I say P and Q. All right. So let me just write down the table. So I have P, I have Q, and then I have what? P and Q. Since I already have the truth table in terms of P and F, I'm going to basically write down the table in terms of 1 and 0s. Okay. And there is a way to get all the possibilities. So suppose if you have two variables like P and Q, then what you're going to do is you're going to first take the first one, and then you basically have 1, 1, 0, 0. Okay. And then you will have 1, 0, 1, 0. All right. So these are all the possibilities, right? So P is true, then Q can be true or false. If P is false, then Q can be true and false. So there are four total. How many possibilities? 4 possibilities, right? So the easy way to enumerate all this possibility, because at the end of the day, you're analyzing all the possibilities, right, together. Is that making sense to you? Yeah. You're analyzing all the possibilities of P and Q, P, statement P separately, statement Q separately, and what does it do to the and? Okay. So again, P and Q is So this is basically P and Q is true only when both of them are true, right? Or otherwise it's all what? It's false. In terms of zeros and ones, this is basically okay. So then this statement has a, so again, note at the end of the day, your combined statement P and Q itself has a true or false value associated with it. Does it make sense? Yeah. For example, look at this example. Today is Wednesday, and today is raining. Yeah. So at this moment, it seems like P is true, right? And then today is raining is also true. So we have what? T and T. So the statement value has what? This whole statement has value what? T. Okay. Suppose tomorrow I come and do the same problem, then the statement will be what? Today's Wednesday would be false. It might be raining or may not be raining, doesn't matter, but false and anything will be false. Okay. So this is the idea behind the conjunction. Again, one should realize, why are we doing all this? We are trying to do all this because in logic, what we have is we have some primitive statements. They are the building blocks. And then you combine these primitive statements, basically using many of these logical connectives. And then you try to associate whether values to them, whether they are true or false. Is that okay? So that is the whole motivation behind this game. All right. Let's go to the next step. The next one is disjunction, or it is called OR. Okay. So a statement, again, we are combining two propositions, P and Q. The statement P or Q is a proposition. It's called disjunction of P and Q. Yeah. So it is read as, when I read this statement, I say P or Q. Okay. So now let's try to analyze all the possible cases we can have. Again, in terms of T and F, I already have it here. In terms of zeros and one, let's write it down. So I'm having P or Q. So again, I need to construct all the possibilities, right? So there will be what? So there are two statements. So two possibilities for P, two possibilities for Q. So total number of possibilities is 2 times 2, which is 4. Okay. So let's construct them in a nice way. We have 1, 1, 0, 0. Then we have 1, 0, 1, 0. Okay. So I'm constructing them in a particular way. You will say, do I always need to do this way? The answer is no. But then you will have to be careful. Oh, which one did I miss? Right? So that's why it's easy to have a algorithm of your own and then construct it. So now, what is the disjunction basically is the following. It is true if either one of them is true. Yeah. Or it is false only when both of them are false. Okay. So we have what? 1, 1 would be, is one of them true? Yes. Here also one of them is true. Yes. Here also one of them is true. False. So this is what? This is the statement for what? P or Q, also called as disjunction. Now let's look at an example again. Today is Wednesday or today is raining. P or, okay. So in this case, both of them are true. So the OR of this will be what? True. Yeah. Suppose if I change this, so suppose I say today is Sunday. Yeah. Or today is raining. In that case, what will be the statement value for this one? The whole thing would be still true. Why? Because this is false. Because today is Wednesday, we are operating on that premise. And this statement has value true. So therefore, we get true. Okay. So this is the, so again, I want to emphasize on the fact that this whole logic business is about assigning the values of true or false to compound statements, the statements of combination of statements. Okay. So 2 of them done, or actually 3: negation, conjunction, which is and, disjunction, which is or. Okay. Exclusive or. Yeah. So there is one thing interesting about a mathematical or. In mathematics, if I say I will have apple or orange, it means I can have apple or orange or both. Yeah, which is different from our English. In our English setup, when we talk about or, we are actually talking about exclusive or. Okay. So what is the meaning of exclusive or? Exclusive or means, or it's also called XOR. In XOR, basically, again, so if you have two statements, XOR is true only if one of them is true. Otherwise, it's false. Does that make sense to you? So that is what is called exclusive or XOR. So in exclusive or, what you want is either this or this. You don't want both of them at once. Okay, that's the difference between or and exclusive or XOR. Okay. So again, let P and Q be propositions. The statement P exclusive or Q is a proposition denoted by P exclusive or Q. It's true when exactly one of them is true. Yeah. Otherwise, it's false. So let's write down in terms of. Let's write it down in terms of zeros and ones, because true and false is already done here. Again, I'll generate. Let me try to generate in a different way, but again, you can generate it in whatever way you want. I generally prefer the way I have been doing so far, but you could also do 0, 0, 1, 1, 0, 1, 0, 1. See, yeah, but there has to be a mechanics of basically enumerating all of that, right? So just to keep the parity with this, I will generate it in the older way I've been doing so far. So let's do this. So again, I'm going to generate it in 1, 1, 0, 0, 1, 0, 1, 0. Okay, that takes care of all the possibilities. An exclusive or is true when either one of them is true. Exactly, sorry, when exactly one of them is true. Otherwise, it is what? So this is a truth table for exclusive or. Yeah. So again, so today is sunny or today is raining. Suppose I hide this. Yeah. Still, this statement is about exclusive or. Why is that? Because they cannot be sunny or raining at the same time. Yeah. So in this case, it is what? If you consider today, right now, outside, basically this one has value false. This one has value true. Therefore, the value of this is what? Okay. All right. So again, you are seeing all these connectives are between two statements, and then later on you can have statements of statements and combine them. Let's have the next one, which is called implication. So again, implication is about two statements. You have P, you have Q. Yeah. And the statement is read as if P then Q is a proposition. It's called implication. Yeah. So the implication is what? So P implies Q. And the idea is it's only false if false implies true. If false implies true, then the statement value is false. Otherwise, it's always true. Okay. Yes. True implies, sorry, my bad. It's actually other way around. Yeah. You're right. Thanks. Yeah. So the statement is, thank you. So the statement is actually, if true implies false, then it's false. Otherwise, it's always what? True. No, so here, let's write it down. So this is false if we have true implies false. Otherwise, it's always what? Otherwise, it's always true. So this is what the implication statement. All right, let's write down the table for it. So how will the table go? We have P, we have Q, and then we have what? P implies Q. And let's write down the values of it. Okay. So again, I'll generate all the possibilities. So let me just do true and false this time. True, true, false, false. Then I have true, false, true, false. All right. And we said that if true implies false, then it's false. Otherwise, it's always what? True. So this is what? This is the this statement is basically called implication. All right. Now, in this case, P is called the premise and Q is called the consequence. Yeah. One is called the antecedent and the other one is called conclusion. Okay. So, all right. Now, note very interesting fact. P, all these statements are what? If you have P or Q or P, they are same. Huh? Here also, if you have and P and Q or Q and P, they will give you the same result. But here we don't have the same thing. Okay. Yeah. So just one thing to know, right? Is that okay? True implies false is false, but false implies true is basically. So far good. Okay. So let's look at this example. If I am taller than 5 feet, then I'm taller than 4 feet. Yeah. So what is the truth value of this statement? Let's work it out. Okay. So if I'm taller than 5 feet, this statement could be either true or what? If this is true, then I'm taller than 4 feet. Okay. So what do you think is the value of this statement? True, right? Suppose this statement is false. I'm taller than 5 feet. That's false. Then in that case, we'll have what? False. So this is an example of what? Of a implication. All right. So this is how the truth table works, as we saw earlier. P, Q. So we have TT, TF, FT, and FF. So it's only false when true implies false. Otherwise, it's always true. Okay. So this is called implication. There are a few more ways to talk about implication. It's not directly like if P implies, like P implies Q. Some people say if P, then Q. You can say P implies Q. P only if Q. P is sufficient for Q. Q if P, in the other way around. Q whenever P. Q is necessary for P. Okay. We don't need to worry about all this, but like, we have some intuition about, because these are all English statements. So we need to know basically what do they represent. Okay. At least some of them. All right. So now the next one is biconditional. So again, we are connecting two statements. Yeah. So we have statement P, statement Q. Those are our propositions. Again, I'm repeating over and over again. They need not be what? They need not be primitive. Okay. Yeah. Because right now we are dealing with all the primitive ones, but they did not be primitive. All right. Because that's how we'll combine more and more complicated statements. So biconditional is basically biconditional statement is a statement which has truth value only if both of them are true or both of them are false. Okay. So again, how will it look like? I have P, I have Q. So let's do zeros and ones again. P, Q. We have 1, 1, 0, 0. We have 1, 0, 1, 0. And then we have biconditional P and only Q. Let's see. So we have what? 1, 1. So what will that give us? 1. 1, 0 will give us 0. 0, 1 will give us 0. And 0, 0 will give us what? 1, 1. Yeah. Why? If they have same truth value, P and Q, then the value is 1 or it's true. Otherwise, it is false. So this gives us all the. So these are, this is so-called biconditional. All right. So it is read as P if and only if Q. Yeah. In mathematics, you will see a lot of theorems later on. Like, for example, if you have seen some result already, say, for example, if you take ax squared plus bx plus c, the parabola opens upward if a is less than upward if a is greater than 0, for example. Statements like that. So these are all mathematical statements, right? So in mathematics also we use logic a lot. In fact, so a lot of theorems, proving basically it relies on what? On mathematics. All right. And also sometimes you can have many complicated statements combined together, but the way they are combined, no matter what, their value could be always true. Yeah, it depends on how the statements are combined, right? Okay. Now let's talk about converting an English statement into a bunch of logical equivalent statements. Okay. So let's look at the following statement. So getting an A on a final exam and doing every exercise in your textbook is sufficient for getting a what? A in the course. Correct. So there are a bunch of statements here, right? So getting A in the final exam. So that is one statement. All right. So P, let's take P. I mean, like, there's no reason why I chose that to be P. We could have chosen anything. So P is a statement of getting A in the exam. All right. Let's look at another one. Q, doing every exercise in the textbook. Yeah. And then we have what? Another statement, which is what? R, getting what? A in the course. So we took P, Q, and R are these statements. All right. So now question is, how are these statements? If I take the above English statement, yeah, what is the logical equivalent of this statement in terms of P, Q, and R? Okay, that's one. Right. So how do we go about it? So look at this one, for example, getting an A in the final exam and doing every problem in the textbook, right? So for sure, we have P and Q here, right? You agree? Because those two are connected with an and. And then we have what is sufficient for getting A in the course. So now let's see what is the sufficient. What is the word sufficient? Right? So if you go back here, it says what? P is sufficient for Q, isn't it? So it says, so now if we consider this, P implies Q means P is sufficient for Q. So here you can see that doing what? Getting A in the final exam and doing exercise in the textbook. This is your statement. This is sufficient. That means this together implies what? So this is how you can convert a English statement into basically into a logical, correct? Mm-hmm. So right now we are not assigning any truth value to this. Yeah, it's not a matter of whether it's true or false at the moment. We are given an English statement and we are converting that into what? Into a logic statement. Yeah. So whether it's true or not, we don't know, right? I mean, like, because we don't know the course policy, for example. You know, for example, if final exam is only worth 10%, let's take a random example. Whether you get A or not, it's very likely you will fail the course, for example, right? Or if final exam is 100%, yeah, then the other statement becomes redundant, really, right? So these are the ways basically. So it depends on the policy, really, right, of the course. So the idea here is to convert the statement into a logical statement. Whether it's true or not, that's another story. Yeah, we are not assigning the values to it yet. Yeah, is that making sense to you? Yeah. All right, so you can do the other example. Now, so let's talk about a compound statement. So, so there are two statements which are so-called tautology and contradiction. Okay. So what is a tautology and what is a contradiction? Again, these are Greek, Latin actually words. So tautology simply means the following: the statement will always true no matter what. Okay. So if you have a statement P or proposition P, it will be made out of individual statements. Okay. And the idea is no matter what the individual values of statements are, the output of that statement will always be true. So such a statement is called a tautology. Let me give you an example. Okay. A very simple example. Let's take P. Let's take this statement, negative P or P. Okay. Look at this statement, negative P or P. Okay. We agree that this is a statement, right? Yeah. Now, no matter, so this statement is basically it's a compound set, right? So no matter what the values of these are, right, the output is always going to be true. Let's check it out. Okay. So such a statement is called tautology. Tautology means it's always true. And note that it doesn't need to be only two statements. It could be many statements combined together, right? So for example, let's look at the truth table of this. So again, we have P, we have negative of P. Now, how many variables are here? There's only one variable, right? So what are the possibilities? So then in that case, we can take 1, 0. Yeah. Then we have negative of that will be 0. Yes. So now when you do negative P or P, it's always what? It's always 1. So this is always true, no matter what P and Q, P and negative P's are, right? So such a statement is called tautology. So this is a tautology. Yeah, because output is always what? Or 1. Now you say, what is not a tautology? Well, you can see that all these things were not a tautology, right? They are not true all the time, right? So this is not a tautology. Okay. Now contradiction is exactly opposite of tautology. So what is a contradiction? Contradiction is always false, no matter what. So such a statement is called contradiction. Yeah. So contradiction would be an easy example to construct would be, let's take P. So let's take negative P and P. Right. I'm just constructing some examples on the fly. We'll see some other examples too, slightly more fancier examples. And you will see that those statements also can have, like, we can discuss whether they are tautology or not. So negative, so we have P, then we have negative P. That's how the statement is made. So again, here, because we have only one variable, so we can take 1, 0. In this case, negative P will be 0, 1. And then you can see negative P and P. So in this case, it's going to be 0. In this case, again, it's going to be 0. So this is a contradiction. Yeah. And if a statement is not a contradiction or a tautology, then it's called contingency. Okay. All the other statements you saw earlier, like P or Q, P and Q, they are all what? Contingency. Because, well, they're not always true. They're not always false. Contingency in some sense means that it depends, kind of thing. Okay. But whereas tautology is always true, no matter what. Yeah. So far, good. Now, let's talk about logical equivalence of two statements. So two statements are logically equivalent if their truth table looks exactly the same. Okay. Or two statements P and Q are logically equivalent if P by implication Q, by condition, right? So I'm reading this as P if and only if Q is a tautology. Let's construct an example for it. So this is where one interesting example. So two statements are logically, so two propositions P and Q are logically equivalent. I want to show you an example where two statements are logically equivalent. So with the two examples. So let's take P, let's take P, Q, let's take P implies Q, and let's take negative P or Q. And then let's take, so I'm trying to show to you that these two statements, this one and this one, are logically equivalent statements. Okay. Logically equivalent statement means what? They have same value for the inputs, or a better way to say that would be that this is always going to be a tautology. That this is going to be, so this by implication is going to be tautology. Yeah. So the idea is if I just call this as A and B, then this by implication is going to be tautological. All right. That's another way of saying that these two statements are equal. Let's check it out. Okay. Let's work out this example and things will become clearer. What it means by tautology, or what it means by logical equal. So again, we have two variables now. So let's construct all the possibilities. So all the possibilities are going to be 1, 1, 0, 0, 1, 0, 1, 0, right? Now let's look at P implies Q. So P implies Q is false only when what? 1 implies 0. Otherwise, it's always true, right? You agree with that? Yeah. So 1 implies 0 is false. Otherwise, it's always true. Yeah. Now let's construct negative P or Q. So again, I need a small table for negative P, right? Because I'm going to basically build it out of, what do I have here? 1, 1. And then I'm going to basically, I want a small table to write down negative P, because that way it's easy for me to see what is happening. Because I'm going to do negative P or Q. So what is negative P? It's going to be 0, 0, 1, 1. So negative P or Q is going to be, let's look at these two tables, okay? So it's going to be 1 here, 0, 1, 1. Yeah, do you see these two tables? They have exactly the same distribution. Yeah. So again, saying two things have exactly the same distribution is not that fancy, right? So the another way to say that they have same distribution is to say that if you look at this as A and if you look at this B, if you look at the by implication, it will be a tautology, right? Because what is a tautology after all? Tautology basically happens when, so if you have by implication, for example, the by implication is true if and only if both of them have same truth value, right? Do you agree? That is same as saying that the distribution will be the same all the time. If one is true, then the other one is true. If one is false, then the other one is false. Does that make sense? So if you look at this, we are looking at A if and only B, where A is this line, B is this. So again, 1, 1, both of them are 1. So by implication will give me 1. Here, both of them are 0. By implication will give me 1 again. Both of them are 1. And both of them are 1. Okay, I'm looking at the table A and B. So you see, P implies Q is logically equivalent to the statement negative P or Q. Yeah, you will say, why do I care? What is the point of this? Now you will be, say, suppose you're given a big set of logical statements. Yeah, then you try to basically, out of that statement, you try to make sense of it, whether it's true or not. And then sometimes you will have to change, say, for example, we'll have to change P implies Q to negative P or Q. Or we may have to change P implies or negative P or Q to P implies Q. Does that make sense? Yeah. It's like changing the equation. It's like saying X plus X. Yeah. Sometimes we replace X plus X as what? 2X, right? Why? Because they have the same values. The same way, if I have P implies Q, if need be, I can just replace it by what? Negative P or Q. Because these two statements are logically what? Equivalent. Okay. So now, how do we show that two statements are logically equivalent, right? So we did one example right away. This method would be naturally called what? We are having a table, right? So this method is called tabular method. Yeah, exactly. We are constructing the table and then we are looking at it. So this is called tabular method. Okay. Now, the other method is called algebraic method, where we are going to use the following laws of logic. So here, again, I'm writing the same thing, what we did just now. We have P implies Q is biconditionally equivalent to, or is logically equivalent to P or Q. Why? Because we are showing that they have same, here is a mistake from my side, right? We have P, we have Q. Let me write negative P. In that case, it will be what? False, false, true, true. And then what is negative P or Q? So let's see, negative P or Q. Negative P or Q, so true. Negative P or Q. Sorry, negative P or Q. So this is false. Then we have negative P or Q. True. Negative P or Q. False. sorry, it's true, right? So there's an error in there's a typo in the notes. But now when you compare these two things, they have exactly what? Same able distribution. Yeah. That means they are logically equivalent. Yeah. So again, let's try to philosophically ask why is that the case? Now, a statement basically, if you take a compound statement, the value of that being true or false depends on the individual inside statement, right? Like, say, for example, today is Wednesday or it's raining. So it depends on the individual statements, okay? Now, when you take two statements and they have like two compound statements like this, and they have same value, it is as if they are what? They are equal statements for us. Yeah. So this is the idea behind the logical equivalence.